DiffDock-PP is the protein-protein interaction version of DiffDock. As that implies, there are other versions of DiffDock that perform different types of docking. The original DiffDock was a small molecule or ligand protein docking problem. So we know the chemical graph of our small molecule. We know how every atom is connected to each other. We know the general structure. We might not necessarily know the exact conformation of that small molecule in which it is binding to the protein, but we know the structure of it. We also know what the structure of the protein itself is. These typically use a fixed, fully rigid structure for the protein, so we're still kind of making that assumption. As you can imagine, also the name implies that we're doing diffusion, so we're diffusing from a completely noised version of this docked complex into a denoised version that should more resemble the data distribution. So as we talked about with RF diffusion, we were diffusing these frames around. In this case, the diffusion space is a little different. We do have a frame, essentially, defining where the center of mass of that small molecule is relative to the protein itself. So you can still kind of move this guy around, you can rotate it, translate it, but we also have these torsional degrees of freedom. So the small molecule has many different conformers that are allowed, so we also sample some of the torsional angles of the small molecule to allow it to be flexible. So as you can see, some of these small molecules in here have different conformations than one another, which allow it to maybe find a particular conformation that works well for a specific pocket within this protein. Once we've got a bunch of structures, ideally, maybe they line up in the same place. If not, that's fine too. But there's usually this confidence model at the end that is used to predict which pose is most accurate. So once we've generated a bunch of them, we score them with this confidence model. Any questions about DiffDock? Yeah?
So is this a rigid body protein, or is it also flexible?
The protein itself is rigid. Small molecule is flexible, though. Okay. They have made an extension on this that performs even better. They call it DiffDock-L for large. It's essentially, so they've done a couple things to make it better. First of which, as you can imagine, the large refers to they made the model bigger. That tends to help. The other thing that they did, which I think is a lot more interesting, is this confidence bootstrapping. So what they did was they performed a rollout. So they made a prediction of the full diffusion trajectory to sample some conformations. Then they used their confidence model that was trained to predict whether this conformation was good or not. And those structures that were good, we want to make that trajectory, the probability of generating that structure, even more likely. So this is kind of really like honing in on the idea that the global docking problem is really difficult. And a lot of the time it's going to be sampling a lot of kind of nonsense that isn't really good positions. So if we can start to really hone in early on in the training process of what a good structure is, a good high confident binding interaction is, we can really improve the performance, and they really do demonstrate that quite well. Okay, questions on DiffDock-L?
So for small molecule and protein docking, why would anyone use something like this compared to Glide or Autodock Arena?
I think maybe speed or something like that. I think right now we're still seeing some advantages to some of the traditional physics-based, energy-based methods for docking. However, yeah, some of the deep learning-based docking tools are more or less in their infancy, but they're still growing quite rapidly.
So is this being validated by those traditional tools?
Yes, they're being benchmarked against those tools. Yeah. Do you have anything else to add to that?
What was the question?
Why use one of these methods versus like a traditional physics-based or?
Oh yeah, a traditional physics-based has the accuracy is like 20%, and then like AlphaFold 3 has like an accuracy of like 40%. It's blowing it out of the water right now.
Yeah, so AlphaFold 2 is still honestly kind of the one of the best docking models we have, which is kind of weird because it's also folding the protein, it's predicting the overall structure, so it's technically also solving the flexible docking problem. But yeah, these other methods, as you can imagine, like have less degrees of freedom, so maybe you can learn better. But yeah, they're still kind of trying to reach that accuracy.
Other thing I will say is there's like an active effort right now to bring energy into current AI models. So once you bring that advantage of traditional based docking into it, like this is so much more flexible.
Okay, I can see that.
Okay, so this is kind of, oh yeah.
I have a couple questions actually. So this is like a redocking method still, right? Like matter where you start your ligand? Does it, or is it pretty?
Not really. It should sample enough like global space where it doesn't really matter where it's initialized.
Gotcha.
It should still ideally find the correct location. Although I don't know how like true that is in practice. That's like ideally.
So that's what they're trained to do. So every time a new trajectory is made, they like put the small molecule somewhere random, so that no matter where it starts from, it should be able to find it.
Okay.
Did you have a question?
Yeah, what about buried cavities?
Buried cavities. Yeah, so that is a difficulty of this because it is rigid protein, but right. During the diffusion process, there isn't anything like restricting overlap between the ligand and the protein itself. So technically, it could like phase through the protein and find an internal pocket. The protein won't open up for it though.
How big can a small molecule be for this? Can you use like a DNA strand, or is that like you're starting to get too big?
I do not know. I don't know the biggest small molecule that they trained on. Shouldn't be too hard to find though. Okay, any other questions?
To which one is a follow-up? Can you write a smiles for DNA? I think just as long as you can write a smiles.
You should be able to.
Has anyone tried this out on multi-state proteins that like have a change upon binding?
Like the apo-holo?
Yeah.
You know, I mean, since it is rigid body, you are kind of like forced to use the holo structure. So yeah, I don't know if there's many people looking at that. It's the difficulty because of the rigid body. Yeah, Ben?
It looks like they only train DiffDock on small molecules, and so they have on their GitHub, we recommend not, using this for DNA.
Okay, cool. This is kind of so it was DiffDock, and then DiffDock-PP, and then DiffDock-L. It was technically like the order in which these guys were released, but these two are small molecule based, and so I wanted to talk about them first. So we'll go into what DiffDock-PP is. It's honestly quite similar. We have the two unbound structures, both still rigid, and we're sampling the transformation between them. So we have that rotation matrix and the translation vector. And as you can see through the diffusion process, we're doing a bunch of global sampling. So this guy is actually the native ligand pose with the native receptor pose. And this is the one that we're moving around, the currently noisy structure. So as you can see, it's kind of sampling around a local space, and eventually coming into the correct location. So it's just denoising the translation, the rotation around the protein to kind of find what the correct interface is. Similarly, they also have a confidence model that is trained to predict whether this pose is good or not, which is essentially just the probability of whether the ligand armistice is less than 5 or not. We'll talk about that also. Okay. Yeah.
And the reverse diffusion process is applied to both structures or just the ligand?
Technically just the ligand, right? Because what they do is center the receptor, and now the ligand is the only really movable part. There are other ways you can parameterize it, but that's how they do it.
Okay, so it's not like flexible?
No. The proteins themselves are rigid.
Is the diffusion process guided by hotspot residues?
No. But you can imagine doing that. Like you can imagine conditioning on the fact that we do know that some residues are interacting with the ligand, which may really bias it. Although they didn't do that with this training process.
Do you know if you get like pretty much the same result regardless of which one you hold constant? Or like do you always hold the larger one constant, or is there any?
That's a good question. I don't know if there is a difference, but typically you hold the larger one constant.
Does this also use like global seed to reproduce the same thing? Kind of going by with the earlier example, you could see like if you wanted to jump to t time step 0.25, right? It's already kind of in the local where it's supposed to be at.
Yeah.
But if you were to say like you were to rerun this again, right, and you jump back at that time point, would it still put you in that same area, or could it have localized to a different?
Right. Yeah, I mean, so these trajectories are stochastic. You can move it back. If you haven't set the seed, then it should still go to a different location, although it'll still be like very minor movements at that point because you're doing kind of a small amount of noise added. Okay, so this is the overview of what DiffDock-PP is. A little bit of performance. This is a measure of a fraction with a low complex RMSD, and then the amount of noise. And as you see, as we start really adding more noise, or sorry, this is, what is epsilon? I don't remember exactly what epsilon was. But so AlphaFold multiplier is this black line, and it's been performing really well. DiffDock-PP is maybe slightly better with 40 samples. That's what this 40 means. Some of these other earlier deep learning-based models like Equidoc have a lot to be desired. But then there's also some of these more physics-based methods like PatchDock, HDock, Attract that perform well for a small amount of distance away. I think this is like distance away from the native. So like if it's really far away, it's got to try to find it. But yeah, so DiffDock-PP is doing pretty good, about as good as AlphaFold, at least according to this. This is kind of comparing how good the confidence model is, as well as how good the predictions are as you start scaling up the number of predictions. So as you add more generative samples, so at this point, if we're sampling from 0 all the way up to 40 different samples, we get like a slow increase in the number of poses with a low complex RMSD. This top one is given the confidence model predicting what it thinks the top one prediction is. So as you can see, there's actually a huge discrepancy between the perfect selection. So the model can actually find some structures that are really good. Maybe more training needs to happen for the discrimination confidence model because there's still this huge gap between these. So if the confidence model was better at choosing the correct pose, then we'd probably have even higher success rates. And this is also similar over here. At this point, we're rejecting complexes. But yeah, so this is like the inverse discrimination task. Like if this is wrong, as you can see, there's still this huge discrepancy between the perfect selection and confidence model. So I strongly believe that the confidence model is probably one of the underperformers in this workflow.
In my hands, across many methods, physical and DL, or diffusion-based, I should say, that discrepancy just seems to be commonplace.
Yeah, I mean, it's a difficult problem. Like, how do you look at an interface and know whether it's correct or not? There's a lot of learning to be had there. And it's probably really useful to see a bunch of negative examples of like what a bad interface is, so you can do some comparisons, but now you need a bunch of extra data and stuff like that. So there are a lot of technical challenges with training a confidence model like this, but as you can see, there is a lot of room for improvement, so that could be a nice future direction.
Are these all for, like, when they're taking the perfect selection, are they all only considering cases where there is only one, like, physiological binding location?
Yeah.
But there's no, like, intermittent spots where it kind of gets, like, stuck on, as it?
Yeah, this is assuming that there's one correct binding interface orientation.
How do they filter for that, I guess, to make sure? Because I guess on the PDB, like, you have some bound structures, but that doesn't mean that it doesn't, like, you know, wander around somewhere or get lost somewhere.
I mean, that's true. It's just kind of an assumption that they make. So they just grab the PDB structures and then like that interaction's the ground truth, only existing interaction there. So yeah, it's not a perfect solution. There are assumptions there, but it's the simplest thing to do.
How much better is this than just folding them using Alpha 2 Multimer? Like,
Yeah, I mean,
is it better to like generate the two things separately and try to dock them, or just to like fold them?
I mean, as you can see, AlphaFold Multimer is, about the same as DiffDock-PP. So in my head, it's just another orthogonal validation metric. So if you like generate a bunch of samples with DiffDock-PP and they start to line up with your AlphaFold prediction, that's a nice like kind of validation reassurance thing. Okay, let's open it up a little bit. So similarly to protein MPNN, they represent their proteins as graphs. So in this case, I have colored 2 different beads on strings representing proteins, this red one and this blue one. They're pretty much identical in shape, so like just arbitrarily called the red one the ligand and this one the receptor. When we're defining this, we have intra-chain edges. So we look at our nearest neighbors, in this case is 20 nearest neighbors, and we add an edge between them so that we can like pass information about the local structure of this region of the protein. So every residue is kind of now looking at its neighbors and getting kind of an idea of where they are, what they are. So they also have amino acid type for this, but each node is represented by the C alpha and some orientation information. Yeah, so there's information about the local structure around each residue within a chain. We also add cross-chain edges. So here, each residue now looks at its 25 nearest residues from the other chain. So this is how it kind of gets an idea of what the other chain's orientation is relative to this residue. And that can really start to guide how they should be moved together, whether it needs to be rotated such that different residues are passing information to the interface residues. So this can really help guide the interactions between them. And so I just kind of showed like for a single residue, but each residue is connected to its nearest neighbors in its own chain, as well as to the neighbors in the cross chain. So there's a lot of like edges and connections here. They use message passing, but they use a equivariant version of it that just really relies on the spherical harmonics, similarly to how the SE3 transformer did. So they take these spherical harmonics to compute equivariant features that they're able to use to update the hidden representations of the nodes themselves. Don't really expect you to know what all that means besides the fact that it's an equivariant architecture, so it doesn't like perform any invariant transformations of the coordinates or anything like that. It just literally kind of uses the raw coordinates and learns from those. The losses that they use are pretty standard for diffusion. In this case, rather than predicting what the final ground truth structure was, like we did in RF diffusion, the main reason we did that is because it kind of like simplifies the architecture. It also like really can leverage the prediction capabilities of Rosetta Fold, which was where we were pre-training this from. However, for this model, they parameterize it in a different way. In this case, we're predicting how much noise was added to the structure. So this is, if you like think about it and do the math, you can see that this is equivalent, but we're essentially at a specific time step, we're trying to predict how much noise was added to that in both the translation as well as the rotation. And then there's just separate losses for each of those terms. And for the confidence model, it's just learning this binary cross entropy on the probability that the ligand RMSD of this pose is less than 5 angstroms. So not like a super strict cutoff. 5 angstroms isn't large, isn't terribly small, but it's also not like exorbitant. So it's kind of a reasonable estimate, but maybe there's a lot more learning to be had there. Losses, any questions on the losses? Ben?
Could you talk a little bit more about what spherical harmonics are?
Most visual way, like for me, is it reminds me a lot of the electronic orbitals of the electron clouds around each in the atoms, because those are also spherical harmonics. So as you can imagine, this is like the S1 sphere of the electrons. These are your p orbitals, and then you have your d orbitals. These are spherical harmonics. They're all spherical harmonics. It's just a way of like decomposing your 3D space into these bases functions that, when combined, can recapitulate the native or your information. So it's a way of like decomposing your information into these bite-sized elements that are like as irreducible as possible. And then once you have those, you can kind of like put them back together. So it's like you're decomposing into the building blocks that you're putting them back together. Okay. Some limitations, like we mentioned, it doesn't account for the flexibility within the proteins themselves. It's just doing rigid body docking. It's also prone to hallucinations. As you can imagine, it can find a wrong interface. There's also not explicitly a loss within the model itself for clashes. However, you can add an extra filter at the end when you're doing like this confidence metric. You can add like an extra term there when you're ranking them, saying if this is overly clashy, just kind of throw that one out.